Jianwei is a presidential chair professor and associate dean of the School of Science and Engineering at the Chinese University of Hong Kong. He is also the vice president of the Shenzhen Institute of Artificial Intelligence and Robotics for Society. He has been an IEEE fellow, an IEEE ComSoc distinguished lecturer, and a Clarivate Analytics highly cited researcher. He is the incoming editor-in-chief of the IEEE Transactions on Network Science and Engineering from Jan 2021. So, Jianwei, it's great to have you. So I invite you to give your talk.
Okay, thank you very much. Okay. By the way, I'm in a hotel room and the Wi-Fi is terrible. I was disconnected several times during Wendy's talk. So if you don't mind, I'll turn off my video during my talk and I can turn on it back again.
Sure, you can do that, Jan. Yes.
Yeah, thank you. Okay. So let me share my screen. Can you see the screen?
Yes, Jianwei, we can see your screen. Go ahead.
Okay, thank you. Okay, thank you very much for the nice introduction. Today I'm going to talk about incentive mechanism design for federal learning in edge computing. So basically, I'm with the Chinese University of Hong Kong, and actually I'm with the Shenzhen campus. We have a new university built in Shenzhen. So this is the Chinese University of Hong Kong, Shenzhen. I'm also with the AIRS, the Shenzhen Institute of Artificial Intelligence Robotics for Society. This is a joint work with my current PhD student, Ning Ding, who is with CUSK, and also Jianwei Huang, who is my former postdoc and now a faculty member at Tsinghua University. So we know that in edge computing, we need to involve a lot of edge devices in the communication and computing. Each client in the edge computing, the edge devices may collect only limited data, okay, to be transferred back to the cloud, for example. However, in many applications, it may be inconvenient, risky, or even illegal to store all the client's data in a centralized location. So federated learning comes to rescue to these cases because it can help to achieve a good computation performance, in particular on a performance for building a machine learning model while mitigating the privacy risks of aggregating all the data in a centralized location. Okay. So what is federated learning? So federated learning is essentially emerging machine learning technique. So this figure illustrates the overall process of federated learning. First, the edge devices, or we call them clients, they can perform local training based on their local data. Okay, so each device has some local data, and they can do some machine learning based on this local data. And then after this computation, they can send the local training model parameters to the cloud. Okay, instead of sending the raw data to the cloud, it's going to send the parameters of the model it has just trained locally to the cloud. And then the cloud is going to aggregate these parameters from multiple clients to build a larger shared machine learning model. And the cloud is going to send the parameter of this shared model back to the clients. So this will be called one global iteration. So this process can iterate and until that's the overall machine learning model that is going to converge at the end. As you can see in this process, there's no raw data exchange, only the models of the trained machine learning models have been exchanged between the clients and the cloud.
Jianwei, sorry for interrupting you. I think your slide is not moving, it's changing. So can you double check?
Really?
Yes. So we are still in
slide 1?
Yeah, you're still in slide 1. Yeah. Can you change now?
Yeah, actually I was changing, but let me reshare. I'm not sure what happened. Okay, let me reshare the slides.
Can you change the slide?
Oh. Now it's in slide 2. Can you see?
No, I think now we have a dark screen. Can you do it again? Can you do it again?
Yeah, something wrong with the changing. Okay, so let me open this PDF file using a different software. Okay, it could be my Acrobat thing. Okay, I apologize for this. Let me share again. Okay, now you can see my PDF, right?
Yes,
Let me go in full screen. Can you see it in full screen?
Yes.
I'm changing the slide.
Yes. Now we are good.
Okay.
Yes.
Okay. Okay, good. Hopefully you didn't miss much. Okay. So now the application of federated learning in edge computing, there are many applications. For example, if you think about these edge devices as self-driving vehicles, then they can collect information as they drive, and they can share this information through this federated learning framework so that they build an overall machine learning model, say predict the traffic, predict the security issues, safety issues on the roads. If these edge devices are drones, then they can explore inaccessible or dangerous areas and send information back to build a larger machine learning model. If you think about this edge device as smart watches or wearable devices, like the wristbands and Apple Watch, they can provide personalized health services to the users without revealing the very sensitive health information collected from each user. So, what are the challenges of implementing this federated learning framework in an edge computing environment? So there are several challenges. First, the clients may need incentive to participate in the federated learning because the participation would involve cost, both due to local computation and also the communication with the cloud. And the second, the clients may have private information that are unknown to the server, to the cloud. And third, that the clients can be heterogeneous with different capabilities, in which case achieving a very good overall system performance may be challenging. So in this talk, we're going to answer two key questions. Number one, from the cloud perspective, how to incentivize clients with multi-dimensional private information to participate in the federated learning. Number two, how does the cloud knowledge of the client's private information would influence its optimal strategies? So let me very briefly talk about related work. Most of federated learning literature has focused on either improving efficiency, enhancing security, or preserving privacy. Very few papers have looked at incentive issues. A few recent work have looked at these important aspects, but with a few limitations. For example, they have been focusing on the one-dimensional private information of the client. They've been focusing on one particular information scenario. So compared with this work, our focus is to consider a multi-dimensional private information scenario. And we're going to consider and compare multiple information scenarios. So let me briefly introduce the system model. Let's consider this federated learning over n clients coordinated by a cloud, sometimes we call it a server. We assume that these clients collect the data, and this data are IID distributed among the clients. So this is the assumption that can be relaxed. These n clients are classified into I types. So each type I has ni clients. And for all the clients within the same type, they share the same two-dimensional private information. So for type I, let's call this two-dimensional private information pi I. So it consists of two parameters. One is the fit I, represents the marginal data usage cost for local training. Basically that for each unit of data you're going to involve in a local training, what would be the cost you're going to involve locally, for example, the energy cost, or the potential privacy leakage cost, okay? Because even if you don't exchange raw data at all, by just exchanging model parameters, you still leak a little bit privacy, but not too much. The second parameter is TI, which is the communication time. Basically, for the edge device to send these model parameters to the server, how much time does it take to reach the server? Now, how do we address the key questions we mentioned before? We're going to look at a contract approach, where the cloud is going to offer us a contract in the following format. So we denote this contract as C. The C includes two components. The first Tmax is a scalar. This represents the maximum communication time in each round. Basically says that for all the clients who agree to participate in the federated learning, if your communication time is larger than this Tmax, then the server is not going to wait for you. The second phi is actually a vector. It has I components we call I contract items. For the I component, phi I is actually a two-dimensional vector. SI, and RI. So this is a contract item for the type I client, or intended for the type I client. So SI means that if you sign up for this contract item, this is the total data size you need to use for local training per round. Now, RI says that if you indeed do this, then this is the reward that the cloud is going to give to this particular client for participate in federated training. Now, when the cloud offers this contract, what should each client decide? He should decide two things. Number one, whether to participate in federated learning. Number two, if he decides to participate, which contract item to choose. As I mentioned that there are I client types and there are I contract items. However, a type I client could potentially choose a contract, let's say 5J. Okay. Later on, we'll see that why this is possible and how to mitigate this potential issue so that each client is going to choose the contract item designed for this particular client. So this is the overall overview of the contract. Now, let's talk about the client's payoff. A payoff of a type I client choosing a contract item 5J is denoted by this U function. So basically, if this client is able to set its model parameter to the server less than the T max denoted in a contract, then his payoff would be RJ, which would be his reward obtained from the cloud because he selects the J's contract item to reward is RJ, minus the theta I, which is local cost per unit data times SJ, which is the amount of data he has committed to used for local training. However, if his transmission communication time is larger than Tmax, he's only going to experience the local cost of training, but he will not get the reward because the server or the cloud is not going to wait for him. So this is his payoff. As you can see, for this client, if you choose different contract item, 5J, 5K, 5L, then he's going to end up with a different payoff function. Of course, when looking at this payoff function, we had several assumptions. For example, we assume there's a synchronous updates, all the clients sending information to the cloud at the same time so that the cloud can cut off at exacted Tmax. We also assume that the communication cost is negligible so that each client only worries about the local computational cost. Now, with the understanding of the client, let's look at the cloud. The cloud worries about two things. Number one, how accurate is the machine learning model? Number two, what is the payment to the clients? Let's look at the computation accuracy. So we assume that each client performs one local computation step per iteration. So essentially, he does one computation, and then he sends the model parameter to the cloud. This is another assumption that can be relaxed. So if all the clients do this in a synchronous fashion, then globally, assuming that each client is choosing the corresponding contract item for this client, so type I client chooses the ith contract item, then equivalently, we can imagine that the cloud as if it's performing a mini batch stochastic gradient descent per iteration with a total data batch size equals B. This B is essentially that all the data used by all the users according to the contract items they have selected. Now with this, and let's do this over iterations, so the expected global model accuracy loss of the entire system can be bounded in the following. So this is as the order of 1 over square root of BD plus 1 over D. Now what is D? D is actually the total number of global iterations. It's the capital T, which is total training time, divided by T max. So this is the number of global iterations. Apparently a larger D, a smaller accurate loss. As we can also see that the accuracy loss is also decreasing in B, right? The more data you use per round, then the smaller accuracy loss you have. The payment to the clients is D proportional to D, which is the number of total iterations, and proportion to the total data that is utilized by all the clients per stage, right? And of course that it is proportional to this RI, which is the contract parameter. So with this, we can put things together. The detailed formulation is not important. It's just a rewriting the previous one with the more detailed mathematics. But the cloud wants to minimize its overall cost W, which is the gamma 1 times the accuracy loss plus gamma 2 times the payment. Gamma 1, gamma 2 represents the trade-off between the model accuracy and the payment. A larger gamma 1 means the cloud cares more about the accuracy loss. A larger gamma 2 means the cloud cares more about minimizing the payment to the clients. Now here there's a parameter Z, which represents the cloud's maximum accuracy loss when no agent participate in the federated learning. Okay, so this is the very brief overview of the model. Next, we're going to talk about 3 information scenarios. The first is the complete information scenario, which is the benchmark, where the cloud knows every client's type. This is not realistic in practice, but it can serve as a benchmark for later 2 discussions. The second is the weakly incomplete information scenario, where the cloud knows the number of clients per type, but doesn't know which client corresponds to which type. The third scenario is the strongly incomplete information scenario, where the cloud knows the distribution of the client types, but it doesn't know the exact number of clients per type. Let's look at first one, complete information. So in this case, even though the cloud knows exactly the type of each client, he still needs to find a way to incentivize the clients to participate, because the client can simply choose not to participate. In order to answer this question, we're going to define a so-called IR, individual rationality. So contract satisfy IR if each type I client obtains a non-negative payoff by accepting the contract item phi I designed for this client. So essentially the cloud can say that, since I know you are type I, please select this contract item phi I. And if this client is going to get a non-negative payoff, he's willing to accept this contract item and participate in the federated learning. So the contract design problem under complete information is for the cloud to choose the contract Tmax and phi in order to minimize the overall weighted cost subject to the individual rationality constraints. The second question for complete information scenario is that now I know the constraint of designing the contract, but how should I measure the impact of choosing one particular contract, one particular client type? So the following lemma says that if the cloud chooses a single type I client, this will be the corresponding cost incurred by this cloud. So apparently this is a function of Ti and theta I. It is increasing both the marginal data usage cost theta I and the communication time Ti of this particular client. Now, why we are interested in computing this cost? Because this cost is going to enable the cloud to rank the clients. And notice that each client is characterized by 2 parameters, theta and t. So to rank the clients based on the 2-dimensional information is not easy. And in general, we don't have a complete order of these vectors. However, now we translate this 2-dimensional vector into a 1-dimensional sequence where each client of a particular type is captured by its cost. So we define this preference saying that a cloud has a higher preference over one particular type over the other, that if the user or the client with a smaller cost will be more preferred by the cloud. Okay, so this is a collapsing the 2-dimensional space into a 1-dimensional space. Now with this, we can actually characterize the cloud's optimal contract under complete information. Let's first define the set of types with the minimum cost. So it's possible that it could be two types of clients, therefore different theta and different t, but they may have the same cost. So let's call this a type set J preference. So the cloud's optimal contract on the complete information is to select a single client type within this set, so that it's going to choose the Tmax equals to the transmission time of this type, and it's going to choose the phi according to the following formula, and then it's going to offer a zero contract for all the other client types. So to summarize, under the complete information, it is optimal for the cloud to only offer one positive contract to a single client type with the minimum cost while ignoring all the other clients. Okay, so with this, let's look at the second scenario, which is the weakly incomplete information. In this case, the platform only knows the number of clients per type, but doesn't know which client is which type. The question is that, in this case, how do I incentivize clients to choosefully report their types? Because that's something that cloud doesn't know. In order to answer this question, we need to define the concept called incentive compatibility, or IC. A contract satisfies IC if each type I client maximizes its own payoff by choosing the contract item phi I designed for this contract for this client. So in other words, that if this type I client chooses any other contract item, say phi j, is going to get a worse payoff. Because of this, then each type client does not have any incentive to lie about his type. So the problem that the cloud needs to solve under weakly incomplete information is to minimize the weighted cost subject to the IR and IC constraints. The result is very interesting. We can show that, in fact, in a weakly incomplete information scenario, the cloud's optimal contract is exactly the same as in a complete information scenario. So in other words, that the cloud owner doesn't know which client is which type, but through design a contract that is both IC and IR, is able to attract the most efficient type and ignore all the other types. This result in general is not true in contract theory. It is true here because the optimal contract under complete information only attract a single type. And that's why that is able to do the same under weakly incomplete information scenario. A final few slides to talk about the strongly incomplete information scenario, which is the most realistic case where the platform only knows the type distribution, PI. PI represents the probability type or probability of a client belongs to a type I, but it doesn't tell us how many users in a particular type. So as you can see, that's the problem he wants to optimize here is to maximize the expected cost for the cloud because it doesn't know how many clients are in each type. He needs to look at the total weighted average. Now, this problem is challenging to solve in general because it's non-convex. Nevertheless, we propose a two-part uniform TPU contract, which is very simple, where the cloud offers two contract items, a positive one and a zero one. Now, each client can freely choose which one you want to take, depends on the comparison of the payoff you can achieve under these two contract items. We can show that the TPU contract is near optimal with a provable optimality gap, and it is actually optimal when the number of clients n approaches infinity. Now, the final slide before conclusion shows a very surprising result. Remember that in a complete information case, we said that we can rank these types of clients based on their cost, right? So the cost is a one-dimensional vector. And in a complete information case, you can only choose the client with the smallest cost. Now, in a strongly incomplete information case, in general, you're going to choose multiple types, not just a single type. You would imagine that you want to design a contract to choose multiple types with among those with the smallest cost. But this intuition is not true. For example, in this particular presentation, some cases, there are 5 types of clients in the system. Some cases it's optimal to choose 4 types, but we may choose these 4 types are not necessarily the smaller 4 types corresponding to their cost. The reason is that in a strongly incomplete information case, we need to trade off the cost with the probability. So if a type of the users or clients have the small probability, then it may not be a good idea to choose it, even if it has a small cost, because with some probability, you may end up with 0 clients within this category. Okay, so let me conclude my talk. So this is the first work on incentive mechanism design with multi-dimensional probability information in federated learning. We propose a multi-dimensional contract with a cloud preference characterization based on the cost, which is a one-dimensional summarization. We investigate the impact of information asymmetry level on optimal cloud strategy, and we will review a counterintuitive results of a non-monotonic client selection with strongly incomplete information. For more details about this work, including analysis of a non-IID data distribution and multi-step local computations, I would encourage colleagues to look at our paper, which is will appear in IQB JSAC series on machine learning for communications and networks next month. Thank you very much.